Bismillahirrahmanirrahim. Assalamualaikum and salam sejahtera to everyone. So let's continue on this topic, which is water in soil, part 1b. Okay, in this video, I'm going to show you video of laboratory testing, okay, and also some example with regards to laboratory testing. Okay, testing to determine permeability parameters can be measured based on laboratory, or also can be made on at site, which is in situ testing. But bear in mind, permeability determined in a laboratory may not be truly indicative of the in situ permeability. So therefore, field testing are normally more reliable because the tests are performed on the undisturbed sample, right? We carry out that at that particular area during that condition, which represent the actual condition of soil. However, okay, it is a common procedure as well to collect a sample and bring back to the laboratory and get the rough idea of what are the permeability value of that particular soil encountered at site. For this course, I'm going to discuss only on laboratory testing. Okay, if you want to know further about some method to be carried out at field to determine the K value, which is permeability value, you can just Google in the YouTube and you can just refer to any reference book, okay, on field testing. Okay, but here also I also listed here there's a few methods that can be carried out at field or in situ. Okay, to determine the K value, okay, your K value, which is permeability value, you have pumping test. You can also carry out bowl test, a tracer test, and some other methods that are not listed here. But again, for this course, we only discuss in details about laboratory testing. So for laboratory testing, okay, to determine the K value, you have two methods. Okay, you can carry out falling hot test or also constant head test, but bear in mind each of them has their own preference. Okay, for example, like for falling head test, okay, for falling head test, most likely, okay, we will determine the K value for fine grained soil, so such as what, silt and clay. But for constant head test, okay, then this one will be opt for coarse grained soil, such as sand and also gravel. Okay, it is suggested, okay, it's suggested to been tested, okay, for that particular type of soil. Okay, it's very easy for you to remember. Okay, falling, which is F for fine, F, okay, F for F, constant, C for coarse, so C for C. Okay. Okay, let's look at this video. This video is actually I get it from the internet, prepared by Carleton University. So in this video, you have you're going to watch both testing, which is constant head test and also falling head test, and at the same time, you also will see how actually the data from those results from those experiment being analyzed, okay, based on falling and also based on constant head test. And you will also see that for each of the testing, to get the K value, which is permeability value, they have a different equations. Okay, for falling head test, okay, they have their own equations to get the K value. The same thing also for constant head test, but the concept is almost similar. Okay, you are looking on the velocity. Okay, you are talking about velocity because remember, for determinations of permeability, it is actually based on two laws, which is Bernoulli's equation and also Darcy's law. So each of them, we have a quantity of water being collected at a certain time, okay, for a given time. So you have the time and also identify the heat loss. Okay, okay, let's watch the video.
This is a tutorial for the Hydraulic Conductivity Lab of the Geotechnical Engineering course Civ E 3208. The purpose of this lab is to determine the hydraulic conductivity of a soil sample. Hydraulic conductivity is a property of the soil which determines the rate water will pass through it. It is important to be able to know how to measure hydraulic conductivity, as it is a factor in applications like dam and landfill design. There are two types of hydraulic conductivity tests: the constant head test for coarse-grained soil like sanded gravel, and the falling head test for fine-grained soil like silt and clay. This is the apparatus for the constant head test. Connected to this reservoir are three lines: an intake, which is connected to a tap and will keep filling our reservoir; a discharge line, which will take extra water out of the reservoir and keep the water level constant; and a line with a valve which connects to the test cylinder. First, obtain about 1 kilogram of coarse soil and place it in a container. This should be enough to fill the test cylinder. Record the mass of the container plus the soil in a table. Place a screen at the bottom of the cylinder. This prevents the soil from being carried out. Fill the cylinder with the soil sample. Split the soil into about 3 layers, and compact each layer with a hammer, like this. If your objective is to determine the conductivity at a specific density, measure the mass required given the volume of the cylinder, and compact the sample enough so that it completely fills the cylinder. The top surface of the soil in the cylinder should be level with a small space for the screen and end cap. Place the screen on top of the soil as well as the separator. Next, place the cap on top of the cylinder and secure it with 3 screws, like this. Record the mass of the container plus the remaining soil. Connect the intake line from the reservoir to the barb at the top of the test cylinder, and connect the tubes for the 2 manometers to the 2 outlets on the side. These are for measuring pore water pressure at specific points. Before filling the reservoir, close the valve on the intake for the test cylinder. Turn on the tap and let the reservoir fill up. Once the level of water in the reservoir reaches a certain level, it will start to discharge into the sink. When this happens, the level of water is constant, and we can begin the test. Now open the valve to let water into the sample. Before we start measuring flow rate, we need to let water run through the sample. This is to remove any trapped air. Let the water run through the system for a few minutes. Here we can see the pore water pressure being recorded on the 2 manometers. Now we can start measuring water flow rate. Take a beaker like this one, then measure and record its mass in the table. We'll be using this stopwatch to record the time. Simultaneously start the stopwatch and begin filling the beaker with the discharge from the test cylinder. Here we are aiming to collect about 300 milliliters of water. Simultaneously stop the stopwatch and remove the discharge. Now record the mass of the water plus the beaker, as well as the time it took to fill, in seconds. Empty the water and zero the stopwatch to reset. Repeat this test 2 more times, each time aiming for a different amount of water. Before we finish, we need to calculate the head applied to the sample. To do this, measure the total head at each manometer from the base of the cylinder. Here the head height of the top manometer is 49.8 centimeters, and 11.3 centimeters for the bottom manometer. Finally, record the difference in height between the outlets to the 2 manometers. You can draw a line around the outside to help you do this. In our case, this was 16 centimeters. We can now clean up the apparatus and proceed to the calculations. Calculate the cross-sectional area of the cylinder. To do this, take calipers and measure the diameter. From this we get the cross-sectional area, as the section is circular. The coefficient of permeability for the constant head test is given by this equation, where Q is the volume of water collected, L is the sample height, A is the cross-sectional area of the soil specimen, H is the total constant head, which is the difference in head between the 2 manometers, and T is the duration of water collection. Calculate K for each of your 3 tests. And finally, calculate the average of these 3 to get the final value for conductivity. For the falling head test, first we need to put together the test cylinder. Unlike with the constant head test, which uses a screen, the falling head test uses a porous stone. Place the porous stone on the base like this. Now place the tube which acts as the cylinder's walls over top of it. Then thread the end cap with a hole in it onto the 3 protruding screws. Secure it with 3 nuts. This is to create a tight seal. Now obtain a soil sample. Similarly to the constant head test, measure out approximately 1 kilogram of soil into a container and record the mass of the container plus soil. Place the soil in the test cylinder like this, again compacting the soil into about 3 layers. In this experiment we are using a fine-grained sand, although this test is best done with silts or clays. Level the soil at the top of the cylinder. Place the second porous stone on top of it, and then thread the end cap on, securing it like this. Finally, record the mass of the soil container plus the unused soil. The cylinder for the falling head test consists of just one line connected to the test cylinder. Connect the line to the cylinder. Before we can start the test, we must saturate the soil with water. There are 3 valves in the system. Make sure they are all open. Start adding water to the top of the standpipe. A larger funnel can help you do this more easily. As you can see here, water will start moving into the test cylinder and saturating the sample. When water starts coming out of the nozzle at the bottom, as you can see here, we can proceed. If there are bubbles in the pipe, gradually add more water to the system so that the air can be flushed out. Close the valve at the top of the test cylinder so that the water level in the pipe remains constant. If there is water left in the funnel, open and close the valve so that the level of water in the pipe falls to a measurable level. For the first test, use a stopwatch to record the time it takes for the water to drop a certain distance. Start the stopwatch and open the valve simultaneously. Wait for the water level in the pipe to drop a given distance. Close the valve and stop the stopwatch simultaneously when the new level is reached. Record both levels of water, as well as the time in seconds it took for the water level to drop. If the water level is too low, add more. Repeat this test 2 more times for 3 readings in all. This is the equation for the coefficient of permeability when performing the falling head test. Lowercase a is the cross-sectional area of the standpipe. The internal diameter is given to us as 6.6 millimeters. From this, we get the area. L is the length of the soil column. In our case, the length of the column is 16 centimeters. Uppercase A is the cross-sectional area of the soil column. In our case, the diameter of the cylinder is 6.3 centimeters. Therefore, the cross-sectional area is 31.2 square centimeters. T is the length of time taken for the head to drop. H0 and H1 are the total head before and after each test, respectively. Calculate time for 3 readings in all. This is the equation for the coefficient of permeability when performing the falling head test. Lowercase a is the cross-sectional area of the standpipe. The internal diameter is given to us as 6.6 millimeters. From this, we get the area. L is the length of the soil column. In our case, the length of the column is 16 centimeters. Uppercase A is the cross-sectional area of the soil column. In our case, the diameter of the cylinder is 6.3 centimeters. Therefore, the cross-sectional area is 31.2 square centimeters. T is the length of time taken for the head to drop. H0 and H1 are the total head before and after each test, respectively. Calculate K for each test. Finding the average value of K between all 3 of our tests gives us the hydraulic conductivity. This concludes the falling head test and the hydraulic conductivity lab.
Okay, now let's discuss on the example. So prepare like 5 to 6 examples, okay, with regards to constant and also following head test. So we look at the example for constant head test. So look at this question. Question number 1. Okay, a test for constant head test give this value. Okay, the length is equal to 18 millimeter. Area of specimens is also given. The difference between the head loss is 28 mm, which means that this is the difference between before KH0 and after testing. Okay, water collected in period of 3 minutes, so the times, okay, taken to collect 21.58 millimeter cube is 3 minutes. So this one is your Q value. Okay, so remember this is the equations for constant head test. So you have all the value. You have a Q, okay, you have Q, you also have L, you also have A here is already calculated. H also is given, T also is given. So put everything here, you got the K value. Okay, okay, now example number 2. The questions given determine the time required from the coefficients of permeability. K equal to 0.0986 centimeter per second according to following data. So it's already given to you the K value. Okay, K value is already given, but the question asking you to find time, the T value. Okay, and the rest I think is also given. Quantity of water, Q is given, L is given, head between difference between manometer is also given, H, okay, data H, and the diameter specimen is also given. So it's already given diameter, so you have to calculate area pi d square over 4, right? So you calculate this one first, you got the A value, and then just put everything, okay. So you are looking for T, okay. So equation is QLAHT, right? The equations for K based on constant head test. So to get T is equal to QLKAH. Okay, so you have everything, you can get T. Okay, so this is the solutions for example number 2. Example 3, still constant head test. Okay, the following data were collected, determine the average value of K. So it means that, okay, you have to calculate the K value for each of the series of testing. We have 4 series of testing here, 3, 4, I mean that repetitive procedure. Okay, everything is constant. I mean that the diameter of the sample is constant, distance between manometer to tapping point is given, which is this is L. Okay, the only things that difference, okay, that change is the quality collected in 2 minutes, the Q, okay, due to the head loss, and also the difference is manometer. Okay. Okay, the time is constant at T, which means that every 2 minutes you open the inlet, the outlet, you open it, you allow water to flow out. After finish 2 minutes, you stop and you read the amounts of water being collected based on the difference in manometer here. So everything is given here. The same thing also, get the K value for each of them. Okay, K value for each of them, and then you divide by 4. Okay, because you want to get the average value. So here are the solution for example number 3. Okay, now moving to example number 4. Okay, now we are going to analyze the results based on following head test. Okay, so the following data is given. Okay, L is given, diameter is given. Okay, so if you're given the diameter of specimen, which means that you need to find the area first, okay, as usual, okay, because it's cylinder, so pi d square over 4. Okay, cross section area of burette, okay, it's already given to you here. Heart rate head at the beginning and heart rate head at the end, so the difference between these two is 10 cm. Okay, the time required is 20 minutes. So find the K value using following head test equation. So this is the following head test equation. Okay, bear in mind it's different from the constant head test. Okay, you put everything there. Okay, You have to calculate first the A value. Okay, it's already given to you the diameter, but please make sure that the unit is consistent, okay, between the sand pipe and also the soil column area. Okay, and then just put back all the informations, all the data into this equation, solve it, you got the answer. Okay, example number 5. Okay, based on falling head thermometer, mold of 75 mm diameter and 150 mm height is filled with soil height. The internal diameter of burette is 5 mm, so you have to find the cross-section area for this one and also cross-section area for this one, for soil column and also for sand pipe. Determine the time in seconds, so it's asking you to find T. Okay, if given the hydraulic head to fall from 1300 to 50 mm, so the difference on heat is 1250. If the coefficient of permeability is 0.0215, so again, okay, everything is given, but you have to find the T, so you have to rearrange back the equations there. You got the answer. Please do it and check whether the answer is correct or not with yours. Okay, so finish on the example. So here is some of the methods that can be carried out at site, which is in situ permeability testing. Okay, we know that permeability determined in lab may not be truly indicative of the in situ permeability, like what I said in previous slide. So therefore, the field tests are normally more reliable because the tests are performed on undisturbed soil. Okay, other reasons are because of the soil stratification, overburden stress, and also the locations of groundwater table, because the location of groundwater table in these cases, it might not be constant throughout the time. So if let's say you relies on the K value obtained at lab only, it might not truly indicative or represent the actual condition at site. Okay, several field methods for evaluating permeability such as pumping, borehole, and tracer test. Okay, that's all for the first part of this topic. With that, thank you very much. I'll see you in next video.